Well, thank you very much. I'm Roger Highfield of the Science Museum. Thank you so much for coming along to this wonderful event at the Royal Institution, the historic Royal Institution. Now, we all know that there's nothing more enjoyable than seeing a new book from a best-selling author. But tonight, you've got a new book from two best-selling authors. And just to make it even more amazing and mind-boggling, we are throwing in a quantum philosopher for good measure. So welcome to the Long Earth event in association with Forbidden Planet. And I do want to encourage you, if you've got smartphones, take pictures, do tweet, but don't drive people next to you nuts. Now, first of all, it gives me incredible pleasure to introduce Sir Terry Pratchett. Doesn't really need any kind of introduction. Obviously the author of the Discworld comic fantasy novels, and he's sold a mind-boggling 80 million copies worldwide. And just a few weeks ago, he picked up a gong as the author who best captured the spirit of P.G. Wodehouse for his 39th Discworld novel, Snuff. And he has now reached official national treasure status. Now we've got a second best-selling author, Stephen Baxter, also incredibly prolific, an award-winning practitioner of hard sci-fi, and helped a great deal by his degrees in maths and engineering. Now the good news for all you Stephen Baxter fanatics is that when he tried to be a cosmonaut, he was beaten to it by Helen Sharman. And so instead, he's had to churn out these books like Titan and the Time Ships and Moon 6 and Huddle and Mayflower and Megatropic and short stories like Last Contact and many, many more. And in fact, what really blows me away is if you look at the back of this wonderful book, you've got a list of all the previous publications of these two, and it goes on for 5 pages. And is 112 titles. It just makes me want to lie down. Now, into this very rich mix, we're going to introduce Dr. David Wallace. At the end here, a philosopher of physics from Balliol College in Oxford. And it's with David that we're going to start our exploration of the long Earth because of his philosophical investigations into quantum theory, which is our theory of the very, very small. Now, before we get going, I want to issue a sanity warning, okay? Quantum theory throws up all sorts of crazy ideas. You've got those bloody cats that are dead and alive. You've got atoms that know that you're looking at them. And you've got the parallel worlds of this latest book. You've got the many worlds interpretation of quantum mechanics. And in these many worlds, they harbor any and every possibility, as in the long Earth. Now, this idea, which dates all the way back to 57, in fact, might even have roots before that, has been attacked, with some theoreticians joking that it's cheap on assumptions but expensive on universes, and others that it's repugnant to common sense. But in fact, it's championed by David. He's at the forefront of efforts to put forward the many worlds interpretation of quantum theory, and he's even written a book called The Emergent Multiverse. That's another book you've got to dash out and buy. So I'm now going to hand over to David to give us a brief tour to help us navigate through parallel worlds. Over to you.
Thank you, Roger. Okay, I think I first came across the idea of the many worlds interpretation of quantum mechanics probably when I was just a teenager starting to get into physics. And I think it was basically that I'd come across quantum mechanics, which is the best theory of the very small, and I came across the idea that there was this problem in making sense of quantum mechanics or understanding it as a theory of the world, and there were all these interpretations of quantum mechanics which were supposed to be different ways to make sense of quantum mechanics. And one of these interpretations was the many worlds theory, and I thought more or less immediately that that was the one that was going to be most interesting to look at, basically because it was obviously the coolest of the possibilities. But what I was rather surprised to discover a little bit later, and what's driven a lot of my work on many worlds theory and quantum mechanics is that it turns out to be, in a sense, a cool idea, but in a sense, a very conservative idea. Not a kind of radical new thing we add to quantum mechanics, but something that just emerges as almost irresistibly correct when you think hard about the best physics we actually have. And what I'm going to try to explain to you in the next 20 minutes or so is just why that is, why this apparently science fictional idea just seems to be something that's forced upon us by the success of the most effective scientific theories we currently have. And to do that, I'm going to use just a couple of very basic illustrations of how quantum mechanics works. Now, I'm going to give a disclaimer at the beginning. I'm somebody whose original training is in theoretical quantum mechanics and then found that that was a bit too practical and went into the philosophy of quantum mechanics. So I probably wouldn't know an actual piece of experimental equipment if it tried to bite me. So I'm going to try to illustrate with a very kind of schematic picture of how some elementary bits of quantum mechanics works, and I'm going to apologize in advance to anyone in the audience who actually knows the technical details of this for the vast variety of liberties I'm going to be taking in the next few minutes. So here's a very simple setup. We have a laser, the laser generates a beam, and there's some detector which picks up the strength of the laser beam. And we can imagine taking the laser and turning the beam strength down. And as we turn it down, the strength of what we detect goes down, or we might turn it down by lowering the power on the laser, we might turn it down by putting a filter in the middle, one or the other. And kind of at the base of quantum mechanics is the fact that if light were continuous, you'd expect that as you turn down the strength of the laser, the signal you got would go smoothly down as well. And up to a point, that turns out to be correct. But after a point, you find not that the power goes smoothly down, but that you just start finding that the light is made up not of continuous energy, but of discrete chunks. So the detector will, instead of giving you a kind of smooth signal, will gradually start to give you discrete clicks. And the number of those discrete clicks will go down as the laser strength goes lower and lower. But the energy of each individual detection event will stay at the same level. And what we learn from that is that laser light, all light, is made out of particles, photons, which come with a certain discrete chunk of energy. Okay, so far so good. There's nothing intrinsically weird about the idea that light comes in discrete chunks. And now we do something slightly cleverer. Here's the, wow, that was fast. Here's the laser again. The grey thing is a half-silvered mirror, so it just means a mirror that reflects half the light and transmits half the light. So we put the mirror in the beam, we angle it a bit, half the light goes off towards the top of the screen, half of the light carries on. And then we just put an ordinary mirror across so the two beams come over and they cross over, and we put another of these half-silver mirrors in, and we then just put a couple of those detectors at the end, and we put a couple of lasers on them. This kind of setup's called an interferometer. And let's just ask what we might naturally expect would happen in this setup if light is fundamentally made of these particles, these photons. Well, we found that the light was split so that half of the beam went up that way and half of the beam went along that way. And so the really natural thing to think is what's going on is that half of the photons are deflected by the mirror and half of the photons go straight through. So maybe each individual photon has a 50% chance of bouncing off the mirror, a 50% chance of going through the mirror. So if imagine you're a photon in the top beam, you've bounced off the first mirror, you keep going, you reach that second half-silvered mirror, and now you've got a 50% chance of bouncing again and a 50% chance of going on. So a photon that goes the first way is going to turn up either at A or at B, 50% chance of each. And likewise, a photon that goes along the bottom channel is also going to end up 50% at A, 50% at B, equal chance of each. So what we think, given that we know that light is made of these photons, is that we'll have half the clicks happening at detector A and half the clicks happening at detector B. Because it doesn't matter which way the photon goes, it's going to go to A half the time, B half the time. That turns out not to be what happens, not if you set the experiment up right. It turns out, and what this depends on is very sensitively how long those different paths are. It turns out that you can get all the light to go to A, or all the light to go to B, or anything in between. So in the jargon, there's interference between the bit of the laser beam that goes along the left channel and the bit of the laser beam that goes along the right channel. OK, fair enough. So you then think, well, what's going on here is that half the photons go along the top channel, half the photons go along the bottom channel, and the ones that go along the top channel bounce off the ones that go along the bottom channel, and the way they bounce off is somehow dependent on the length of the beam. And if we get them to bounce off each other just right, maybe all the photons end up at A, and if we get the photons to bounce off each other just right, all the photons end up at B, or anything in between. And that would be fine as well. But if that's true, we'd predict that if we turned down the strength of the laser so that only a few photons, or in the limit only one photon at a time, was going through this setup, we'd expect that this interference effect would go away. Because if there's only one photon at a time going through, it can't be that one photon goes this way, another photon goes this way, and they crash into each other. So that's a prediction that we'd make from this idea of what's going on. And guess what? That prediction turns out to be completely wrong. You can turn down the strength of the laser as much as you like. You can send one photon through every 3/4 of an hour if you like, and you still get exactly the same pattern. Let's suppose, say, we've set it up so that all the light ends up at A. Every single photon in that case ends up at A, even if we only send the photons through one at a time. OK, so we think maybe what's going on is every individual photon is breaking in half when it hits that half-silvered mirror. So what happens is the photon goes along, it breaks into a half photon that goes this way and a half photon that goes this way, and the halves of the photon crash into each other in some way. Maybe. OK, this is starting to sound a bit more desperate, but maybe that's right. But the thing is, we can check that idea. So instead of this setup, we do something like this. We'll just put a detector in each beam. And if the photon is broken in half by the half-silvered mirror, we expect that what we get is a half-strength detection on the left-hand side and a half-strength detection on the right-hand side. And that's not what we get either. Turns out, if we send the photons through one at a time, every time we either get a detection at the left-hand detector or we get a detection at the right-hand detector. We never get both. So in other words, it seems that it can't be true that half of the photon ends up in the left-hand beam and half of the photon ends up in the right-hand beam. So what are we left with? And it seems that the only thing we're left with is that somehow the photon every individual photon has to be in the left-hand beam and in the right-hand beam at the same time. And that's kind of weird. But even though it's kind of weird, it's pretty much forced on us by the setup we've just laid out here. And if you go from these kind of illustrations here to looking at the maths of how quantum mechanics works, you find that's exactly what the maths of quantum mechanics is representing. It's representing situations where somehow photons can be here and here at the same time. Or likewise, atoms can be here and here at the same time. Or maybe spinning this way and that way at the same time. OK, but in that case, why don't we ever see that happening? What happens when we actually, if the photon's supposed to be here and here at the same time, why don't we measure photons here and here at the same time? Wouldn't that kind of be another way of saying half the photons here and half the photons there? Well, to answer that question, we have to think, well, the process of actually looking at where the photon is, the process of how one of these detectors works, is just another physical process. The detectors don't work by magic. I mean, for a theoretician like me, they might as well work by magic, but I'm reliably informed that the detectors are made out of atoms and they work according to understood physical principles. And what are those principles going to tell us? Well, the one thing we know about detectors is that they're supposed to detect photons. So if the photon is in the left-hand beam, the left-hand detector had better click. And if the photon's in the right-hand beam, the right-hand detector had better click. So if the photon's in the left-hand beam and the right-hand beam at the same time, the theory ought to be telling us that the left-hand detector and the right-hand detector click at the same time. So that somehow not only is the photon in two places at the same time, but the detector is in two states at the same time. And the classic way of illustrating just how ridiculous this is, and this is probably the kind of thing that you could get away with saying in the 1920s, and these days the RSPCA would not be happy, if you wire up the top detector to some gadget that kills cats, and the bottom detector to some gadget that doesn't, then if we're in a situation where the left-hand detector and the right-hand detector are both supposed to be going off, then we should get ourselves in a situation where the cat is alive and dead at the same time. And that seems to be kind of a problem because it doesn't seem as if we see cats that are alive and dead at the same time. So if that's the case, how is quantum mechanics supposed to work? I've just been saying this is our best theory ever of the microscopic world, but if our best theory ever is predicting stuff that clearly isn't true, how can we think it's our best theory ever? And the answer in kind of orthodox or traditional, if you like, use of quantum mechanics is we cheat. We say, at the crudest level, we say, well, if you look at a system that's doing two things at the same time, it suddenly stops. So if we look at a photon that's here and here at the same time, it suddenly is either here or here, one or the other, not both. And likewise, if we look at a cat that's supposed to be alive and dead at the same time, when we look at it, suddenly it's alive or dead, but not both. And that seems just a little bit disreputable as how a scientific theory is supposed to work. We can get away with it. It gets the predictions right, but if we think our scientific theories are supposed to tell us about what the world's like, we seem to have a bit of a problem. And there's kind of two traditional things you might do to solve that problem. You might call them, if you like, the change the physics strategy and the change the philosophy strategy. The change the physics strategy says, OK, if our best theory tells us that cats end up alive and dead at the same time, there's something broken with our best theory. We better change it somewhere. And the classic way you try to change it is you set things up so that the theory gets the answers right when it's talking about photons being here and here at the same time, but it gets things wrong when you start doing it for big objects, for cats, for detectors, and so on. So basically what the change the physics strategy is committed to is modifying this incredibly successful scientific theory so as to avoid this pathological weirdness of live and dead cats at the same time. The change the physics strategy is really popular with philosophers. and the alternative, change the philosophy strategy, says something like this. You've been thinking about your scientific theory as a way of describing the world, but that's not what scientific theories are like now we know about quantum mechanics. What quantum mechanics is supposed to tell us is that really scientific theories are just gadgets to predict what happens when we make measurements. There's lots of philosophical difficulties with that way of thinking about things. Here's a rather more direct way of seeing why it's a little bit problematic. You probably mostly know we've got this enormous and enormously expensive machine, the Large Hadron Collider, sitting in Switzerland, which is supposed, among other things, to be detecting the Higgs boson. Now imagine it's your job to sell the funding for a project like that to the science minister. So he says, what's this device for? And you say, it's to test our best physical theory. And he says, so is our best physical theory telling us about what's going on in the really small? And you say, no, our best physical theory is just a way of predicting the result of experiments. And he says, so which experiments are relevant here? And you say, particle physics experiments. And he says, so let's get this straight. You want me to build a really expensive device, the Large Hadron Collider, and the reason you want to build it is so you can predict what the Large Hadron Collider does. The change the philosophy strategy is very popular with physicists. OK, but if we can't if changing the physics is a problem and changing the philosophy is a problem, then we seem to run back to the fact that the theory just doesn't seem to make any sense unless we do one or the other, because the theory says that cats are alive and dead at the same time, and it doesn't seem as if we know what it would be like for cats to be alive and dead at the same time, or more accurately, it seems that we do know what it would be like, and it wouldn't be like this. But there's a nice quote, which is probably apocryphal, but it's good enough to be worth having anyway, by the philosopher Ludwig Wittgenstein, who supposedly was walking through the quad in Cambridge and suddenly asked a colleague, why were people surprised at the idea that the Earth went round the sun? And the colleague said, well, it's because it looks like the sun goes round the Earth. And supposedly Wittgenstein thought about this for a while, and then he said, well, what would it have looked like if it looked like the Earth went round the sun? And of course the answer is, what it would have looked like if it looked like the Earth went round the sun is what it does look like. Because the Earth does go round the sun. And this is what things look like. And the lesson from that is, if you want to ask what would the world be like if such and such was true, it's a bad idea to consult your intuitions. I mean, your intuition about what things would be like if you saw a cat that was alive and dead at the same time is probably something like it would be like being really drunk. You'd somehow be seeing double. You'd be seeing a live cat and a dead cat. But intuitions have had a pretty rough ride from 20th century physics, and so that's not a good way to learn what it would be like. The right way to learn what it's like, and this is the real insight that drove Hugh Everett to move towards what later became called the many worlds theory, was to say, what does our theory tell you would happen when you look at a cat that's alive and dead at the same time? Well, suppose I look at this cat. I'm another physical system. I'm just made out of atoms and so on. I'd better obey the laws of physics. The physics say, if I look at a live cat, I go into a, ooh, live cat state. And if I look at a dead cat, I should go into a, oh dear, dead cat state. So what the theory should tell me is, if I look at a cat that's alive and dead at the same time, then I am seeing a live cat and seeing a dead cat at the same time. And if I then tell Roger about it, what I've seen, then Roger is in a being told the cat is alive and being told the cat is dead at the same time. And if someone tweets about it, then their Twitter feed is somehow reporting that the cat's dead and reporting the cat's alive at the same time. And as this kind of goes out, and as more and more physical systems interact with the systems that are doing the observing, you're basically getting two parallel streams of goings-on. There's a stream of goings-on in which the cat's dead, I see it dead, Roger hears me say it's dead, someone tweets that it's dead, the Earth's gravitational field is affected by it's being dead, the newspapers report it's dead, and so on. And there's another stream of goings-on where it's reported to be alive. And because objects interact with each other, because outside quantum labs we can't prevent systems from getting tangled up with other systems, then the result, according to our best physics in pretty short order, is that across the whole planet, across the whole solar system, there are two parallel sets of goings-on, a live cat goings-on and a dead cat goings-on. And because we're outside the kind of very carefully controlled quantum environment in which we're able to get this kind of interference effect, there's no sense in which the live cat stream of goings-on and the dead cat stream of goings-on have anything to do with each other. Well, what is it to say that there's a live cat stream of goings-on and a dead cat stream of goings-on? Answer is to say that there are two worlds. One world in which the cat is alive and one world in which the cat is dead. And so the idea of many worlds isn't something that we've brought into quantum mechanics to sort out the philosophical problems in the theory. It's something that comes out of quantum mechanics itself just by thinking hard enough about it. These aren't worlds in the sense of completely isolated pieces of reality. They're not worlds in, I don't know, maybe the Philip Pullman sense of utterly separate chunks of worlds, or you know, the philosopher's idea of different possible worlds. They're different worlds in the sense that maybe Earth and Mars are different worlds. They're dynamically pretty isolated from each other, but there's no fundamental law of physics that says that makes a distinction between Earth and Mars. It's just that the way the world evolves under the laws of physics just gives us a chunk of reality, the Earth chunk, and a chunk of reality, the Mars chunk, that don't really interact with each other very much, or at least not at the moment. And so likewise, what quantum mechanics is giving us is a breaking up of the world into streams of reality that don't interact with each other very much. Those are the many worlds. To say just a little bit more about how many there are, where they come about, they don't directly come about because I decide, shall I do this thing or shall I do that thing? Because my decisions are not the kind of thing, probably, that's caused by quantum randomness, or at least I hope not. If I decide not to randomly kill someone, I'd like to think that's because I've made some sensible decision not to do it, rather than because some quantum bit in my brain has gone one way rather than another. So I hope there wouldn't be parallel branches where I take crazy decisions. But what will be the case is that any time quantum mechanics magnifies up some small thing to be large, and then we're going to have this kind of branching going on. And quantum mechanics is going to do this pretty much all the time. basically because of a different sexy thing in popular physics, which is the phenomenon of chaos. So lots of people have probably come across the idea that there are physical systems like the weather that depend very sensitively on really small details of what was going on 2 or 3 weeks ago. If that's true, and we've got good reason to think it is true, and if quantum theory is true, and we've got really good reason to think that's true, well, if some atom that's determining what the weather's going to do later is here and here at the same time, then a few weeks later, the weather is going to be sunny and cloudy at the same time. And there's going to be these different streams of reality, one for each of these ways the weather could be. We seem to be in a very bad one, but that's just the way it is. So microscopic events being magnified up to macroscopic consequences happens all the time. According to our best physical theory, every time it happens, we get parallel branching streams of reality. So according to our best physical theories, we live in a multiverse of many worlds. And that's kind of remarkable. So I'll stop there.